Before we can really explore what's going on with infinite sums, let's take a moment to start talking about just partial sums. So for each positive integer k, the sum s sub k, so that's our partial sum, is equal to the sum of n equals 1 to k, which is some finite value, of a sub n, which would be the sum of the first k terms. All right, now that's known as the kth partial sum of an infinite series, and that set of partial sums in itself can form a sequence. And if you look at the sequence of partial sums, you can determine, possibly, if sum is going to converge to a real number, or determine if it diverges. So it's not the best way of determining, but it's a really good way of shoring up a foundation as to what we're doing. So we'll do some example problems with this so you see what's happening behind the scenes, because it's easy to forget when we start getting into all the different tests for convergence and divergence. So starting with our first example here, I have the sum from n equals 1 to infinity of 1 over 2 to the n. And what I want to know is, does this series converge or diverge? All right, well, one thing we can check first is the divergence test. So if we look to the divergence test, and I usually just kind of put this in the corner because a lot of the series that you're going to run into pass the divergence test, and therefore when it applies, it's great. It just doesn't really apply all that often. All right, so we would have the limit as n goes to infinity of 1 over 2 to the n. Well, as n gets large, that means you're getting an exponent that's large. So the denominator of this fraction gets large, but the numerator stays constant. So that would be going to 0. All right, so it passes the divergence test. Okay. And because it passes the divergence test, that means that it could possibly converge, but it's not a guarantee. But because it passes the divergence test, we know that it, for that, I guess I should be careful in saying that if it failed the divergence test, then we know it would diverge. We just don't know what's happening now. All right, so here's the thing. The divergence test works on the entire series, but the partial sums works on individual sequence terms. So, like for instance, here are my sequence terms. So the sequence, which is, whoops, I shouldn't put an alpha there, a sub n equals 1 over 2 to the n. The terms would be 1 over 2 to the first, so 1/2. 1 over 2 squared, so that would be 1/4. 1 over 2 to the third, which would be 1/8. And you can kind of see the pattern here. So the next would be 1/16, 1/32, and so forth. Okay, so there's the individual sequence terms. Now, the partial sums. So the first partial sum is s sub 1. So it's the sum of the first 1 terms. And the first term, so this is where n is equal to 1, so that first term is just 1/2. So the first partial sum is just 1/2. The second partial sum is going to be the sum of the first 2 terms. So that would be 1/2 plus 1/4, which we would do 2/4 plus 1/4 and get 3/4. So 3/4 is the second partial sum. S sub 3, that's going to be the sum of the first 3 terms. So 1/8 is where n is equal to 3. So in effect, it would be 1/2 plus 1/4 plus 1/8. And certainly feel free to take advantage of your calculator here because the fractions will get crazy after a while. But we have 3/4 so far, and then we're adding 1/8 to that. And then you can use math and frac, and it will try to convert it back to a fraction if it can. So in this case it will, so that's 7/8. And that can just save you some time working with fractions. S sub 4 is going to be the sum of the first 4 terms, so 1/2 plus 1/4 plus 1/8 plus 1/16. So what we have so far, plus another 16th. And then, as a fraction, that's 15/16. Now, do we have to write these things as fractions? Not necessarily. Sometimes it's easier to see the pattern of what's going on as decimals. Sometimes it's easier to see as fractions. There's no set rule there. At this point, I think I can start seeing a pattern occurring. So for instance, the nth term here, so S sub n is what we're looking for. So the sum of the first n terms, we want a function for that. If you look at the denominators, 2, 4, 8, 16, they're actually the same denominators as we had in the sequence terms. So that's 2 to the n. The numerators, 1 is 1 less than 2, 3 is 1 less than 4, 7 is 1 less than 8, 15 is 1 less than 16. So that looks like it's all 2 to the n minus 1. So this would tell me the sum of the first n terms, which is cool. We can get a formula for that. And if you can, you're really well on your way of determining whether or not you're going to have convergence or no convergence. Because the overall series sum, what we would do here is we would take a limit as n goes to infinity of S sub n, which is 2 to the n minus 1 over 2 to the n. And let's see, if I divide 2 to the n by 2 to the n, I could rewrite this as the limit as n goes to infinity of 1 minus 1 over 2 to the n. 1 over 2 to the n, that is going to go to 0 as n goes to infinity. So this limit goes to 1. So what that tells me is this series is going to converge to 1. Now let me show you this visually, try and give you a bit more of a visual argument as to what's going on as well. Okay, so we have the function 1 over 2 to the n. So I'll put that in parentheses to be safe. So 1 over 2 to the n. n starting with 1, that's great, and I'll hit update. Okay, so here's my sequence terms. So you can see 1 over 2 to the n, the sequence terms are going to 0. What we want is the series. So here are the series values. So what this represents is the first point is S sub 1. The second point is S sub 2. So it's the sum of the first two values. So this is the sum of these 2 points. This is S sub 3, the third partial sum. So if you add these 3 points, you'd get this as a total. And this is S sub 4, S sub 5, and so forth. And what you can see is these are basically leveling out at 1. And so what that tells me is that the individual terms here of the partial sums is going to 1, and therefore this series is going to converge to 1. All right, so that's how it all works here. Let's look at another example. Okay, the next one we have is the sequence producing a series n equals 1 to infinity of n over n plus 1. All right, so let's take a look and see what happens here. So the individual sequence terms, so I'm going to say a sub n When n is equal to 1, we would have 1 over 2, so 1/2. When n is equal to 2, that would be 2 over 3, so 2/3. When n is equal to 3, we would have 3/4, and so on. So when n is equal to 4, that would be 4/5. And that might be enough to figure out what's happening here. Okay, the partial sums, starting with the first one, is just 1/2. The second partial sum is 1/2 plus 2/3. So I'll just take advantage of the calculator here. So 1/2 plus 2/3, and that gives me 7/6. S3, so I would take the 7/6 that I have so far and add 3/4. Okay, and let's see what that is as a fraction. 23/12. And then S4, it would be what I have so far, plus 4/5. And then I want to express that as a fraction. So 163 over 60. Okay, so it's harder here to tell what the pattern is, and to be honest, I don't really even see one myself, so maybe decimals will be a little bit more revealing. So 7/6, we probably can just scroll up and see, oh, there it is right there, 1.167. 23/12, that was 1.9167. Oops. And 163 over 60, 2.7167. If you look at the distance of each one of these, let's see, 0.5 to 1.1, that's about 0.6. 1.1 to 1.9, that's about 0.8. 1.9 to 2.7, it's about 0.8 again. That's not too revealing. It doesn't look like convergence to me, because if it was convergence, I think we would notice a pattern. We'd see something happening. So if it's not converging, we can try and look at it visually to see more terms, to see if it looks like it might converge eventually. So let's try that. Okay, so we have n over n plus 1. Yes, this is not converging. So these are the individual sequence points, okay? And these are the partial sums. The partial sums are increasing at a pretty steady rate, it looks like. And it might only be steady for a little while. It might, no, it looks pretty steady for good there. Regardless, it's not going to ever converge because it's going to continue increasing at that steady rate. Here's the thing, here's the kicker. If you look back at the sequence terms, we do not have sequence terms that are converging to 0. So this actually doesn't pass the divergence test in the first place. So if we had checked that, and we should go ahead and show that it works here, we could have determined beforehand that this was going to diverge. All right, so checking the divergence test. We can say the limit as n goes to infinity of n over n plus 1. That right there is pretty straightforward in the divergence test. Rational function rules here. Just take the coefficients of the leading terms and divide. So that would just be 1. So therefore, this thing fails the divergence test and the series itself diverges. Okay, so you'll have a lot of different tools in your arsenal when you're trying to prove just general series if they converge or diverge. You'll kind of get into a mode of knowing what to check first. And the divergence test is always the easiest, I think, and always a great thing to just check first, because if it fails the divergence test, you don't have to go any further whatsoever. All right, let's look at the next one. This one's pretty interesting. It is the sum n equals 1 to infinity of negative 1 to the n. If you look at the sequence terms, what happens here is negative 1 to the first power is negative 1. Negative 1 to the second power is positive 1, because when you square a negative, you get a positive. Then you get negative 1, positive 1, negative 1, and so forth. And it just oscillates here. Now, I'll go ahead and state, if we apply the divergence test, the divergence test fails. All right, because the infinite limit of the sequence terms does not equal 0. All right, so this really doesn't have any hope at all for convergence, but I want to show you what happens. The individual partial sums, we would start with negative 1, and then the sum of the first two would be 0, because negative 1 and positive 1 cancel. Sum of the first three would be negative 1 again. Sum of the first four would be back to 0. So it would just oscillate back and forth here. And then that also tells us this diverges. So this sequence and series diverges. Like, there's no question about this. I just want you to see it, however, because sometimes we run into different examples kind of like this. Let's look at it graphically real quick. Okay, so I have negative 1 raised to the nth power. Now, generally, if you use negative 1 to the x power and try to graph it, you'll get error messages likely. It's okay here because we're only evaluating these things at integer numbers. All right, so I'm going to scroll here so you can see this a little bit better. All right, so the light blue points are the sequence values. So the sequence values, if I turn off the series, you can see are either negative 1 or positive 1, negative 1, positive 1, and so forth. All right, now if you take the individual sums of the first n or the first k values, you get this pattern. So negative 1 plus 1 gives me 0, plus negative 1 gives me negative 1, plus 1 gives me 0, and it just oscillates between those 2 points. But in no way does this converge. So definitely a divergent. All right, let's look at another one that's got a little more chance here, because this one failed the divergence test from the get-go. This next one, if I do the divergence test, let's take a look here. We have 1 over n times n plus 1, and I want the limit as n goes to infinity of those sequence terms. Well, the numerator is not growing, the denominator is growing, and so the value of this fraction ultimately would be 0. So this passes the divergence test. So that tells me that this could converge. All right, we still don't know, but it could. All right, the individual sequence terms. Let's see, when n is 1, this would be 1 over 1 times 2, so 1/2. And then when n is 2, this would be 1 over 2 times 3, so 1/6. When, I should state these, n equals 2. All right, so n equals 3, it's 1 over 3 times 4, so 1/12. when n equals 4, that's going to be 1 over 4 times 5, which would be 1/20th. And hopefully that's enough to see what's happening. All right, the individual partial sums here. So the first one term, that sum is 1/2. The first two terms, we're doing 1/2 plus 1/6, and I'll just do it in the calculator. All right, so 1/2 plus 1/6, that gives me 2/3. All right, S sub 3. So that's going to be 1/2 plus 1/6 plus 1/12. If I add those all together, just take what I have so far and add a 12th. Oh, that's 3/4. S sub 4, we would add the first 4 terms. All right, let's see what happens when we add 1/20th to that. Okay, looks like we get 4/5. All right, now it looks like we are getting a sequence that's pretty predictable. I think we can say here comfortably the numerators are just increasing by n, and the denominators are increasing by n plus 1. All right, so the limit of the partial sums, that's going to be what the value of the limit of these terms are. So this limit is going to be 1, so that tells me this sum is going to converge to 1. All right, now this really isn't a technique we would use to solve sequences in series, but it does give you an idea as to what's happening. I want to do one more here in this video, and this is a very common sequence that's studied here, and it was actually one that was kind of baffled mathematicians for a while. So the first thing is, if we want, this is called the harmonic series, and it's defined as the sum of the first n terms of 1 over n. All right, so it's not the sum of the first n integers, but it's the sum of 1 over each integer. All right, so I want to prove that it diverges. It was long suspected that it diverged, but it took a while to come up with a proof of that. So here's the thing. If we apply the divergence test, it passes. It's pretty readily seen that it passes because the sum of n equals 1 to infinity of 1 over n is 0. So it passes the divergence test. Now, if it passes the divergence test, that doesn't mean that it converges. All right, what we need to do is we need to look at the first, k sums. So like the partial sums S sub 1 would just be 1 over 1, which is 1. S sub 2 would be 1 over 1, which is 1, plus 1 over 2, which is a half. So this is 1.5 or 3/2. The sum of the first 3 terms would be 1 plus a half plus a third. All right, so then if I add those together, 1 plus a half plus a third. That, as a fraction, would be 11/6. The sum of the first 4 terms. So 1 plus a half plus a third plus a fourth. So if I add 1/4 to this, I get 25/12. And if we continue, it's actually really difficult to come up with a pattern here. So if we can't come up with this function determining a pattern, telling us what the nth term is, then we aren't able to take a limit of these values to see if it's converging or diverging. So even this method doesn't really work, and that's why mathematicians were a bit baffled by it. But after a while, someone came along and came up with a proof. And I want you to see this proof because I want you to understand what it really takes to, show some of these theories actually converge or diverge. Would you need to use something like this in class? Absolutely not. But I want you to see historically, what mathematicians had to do in order to prove this. So here's the idea. Someone came along and decided that the sum of the first n terms would look like 1 plus a half plus a third plus a fourth plus and that was supposed to be a fifth there, sorry. A fifth plus a sixth plus a seventh plus an eighth and so forth. That's what it had to look like, okay? But they were having trouble identifying what the sum of that was. But when it comes to convergence and divergence, it doesn't really matter a lot of the times what the value is that it's converging to or diverging. Well, if it diverges, it's infinity, but you just need to show that it converges or diverges. So you can compare it to like other sequences. All right, so for instance, here's what he did. He said that this would have to be greater than a subseries like this. So it would be 1 plus a half plus a fourth plus a fourth plus an eighth plus an eighth plus an eighth plus an eighth plus a 16th, and then so forth. All right, so he did subseries like this. So the 1 and 1/2, those just match up perfectly, but these two values became a subseries matching up with 1/4 and 1/4. Clearly, the sum of 1/4 and 1/4 is less than the sum of 1/3 and 1/4 because 1/4 is less than a third. This was a subseries, and all these eights, the total sum there was less than the total sum here. All right, so he decided that the original series was definitely greater in value than this series. So he's comparing it to another one. But what's cool about this other one is all these subseries. 1/4 and 1/4 gives you a half. 4 times 1/8 gives you a half. If you do the next 8 16ths, you'll get a half. So basically what he's done is set up an argument where he's got all of these subseries adding up to a half. So if you're repeatedly adding a half over and over and over again, so if you continually add 1/2 an infinite number of times, guess what happens? It diverges. And if that series diverges, and then this one's even larger in value, well, this one's also going to diverge. So this was a big result for the time, that there was a proof that the harmonic series diverged. It diverges very, very slowly, but it does diverge. Now, obviously, I wouldn't expect you to come up with an argument like that to prove convergence or divergence, but I want you to take this result and use it because some of your problems will have something similar to a harmonic series, and you'll be able to use a comparative test and state, hey, this is very similar to the harmonic. The harmonic diverges, therefore this one diverges as well. That'll be something that we do in the class. All right. couple of properties. You can read through these. It only works for convergent series, but if you have a convergent series, you're able to do split things up by addition, subtraction, or constant multiplication. If you find that a problem is easier by splitting something up and you're fairly certain that it will converge, you can use these. They probably won't show up a whole lot in the class, but if they ever do, you've got them to use.